Let's take this a little bit further. Look at the conservative quantity like theta. So now we can better explain this idea of moving poleward and upward, or equatorward and downward, right? So you have potential temperature here, very poor quality figure, unfortunately. So you are increasing as you go towards low latitudes and increasing as you go up in the atmosphere from the surface. Remember, d theta dz was a positive slope as opposed to the temperature, which was a negative slope. So towards the pole, warmer latitudes, you are increasing theta at the same height or same pressure surface, and you are increasing as you go up in the atmosphere. So, but it makes it easier to think about cold air coming down, warm air going up, except how can it be done? That's the key question. So this heuristically explains it, kind of what we looked at in the incompressible fluid with no horizontal gradients. So if you exchange air parcels between 1 and 2, okay, conserving, then you obviously will conserve potential temperature because the atmosphere is stable to dry processes. And if you move along this line, it is basically parallel to the constant theta line, or the isentropes. So isentropic movement tends to be conservative as well. And if you move along this horizontal direction, you will just increase potential energy and not release potential energy. So basically we are looking at motion direction needed that can actually reduce the potential energy, not increase it and lock it up or leave it unchanged. Okay, so in a very hand wavy argument, you can show that when there is exchange of air parcels 1 and 2 adiabatically along this sloping line, which is greater than horizontal but less than the slope of the isentropes, then you actually end up reducing the potential energy. So it means you are going to release the available potential energy. Read the book carefully for the arguments to make sure you understood it properly. So theta 2 is greater than theta 1 vertically along this path in A. So PE is just increased when you do these exchanges adiabatically. The horizontal exchange produces no change in potential energy. And path B, with the parcel moving up at an angle higher than theta than the parcel moving down, is what will release PE. Okay, so that's the key point. Path B, the parcel moving up, because the slopes are different, the path moving up is going to be steeper than the parcel moving down. Just connect it back to our idea of warm air moving poleward and up, cold air moving equatorward and down, and combine it with the angles of the potential here. Okay, so whether you're coming down or going up, the angles are going to be different, and that's going to be the key to reducing the PE, which means producing kinetic energy. Okay, large scale atmospheric energy and momentum budgets. In this case, now there must be a conversion of energy into kinetic energy from available potential energy gained from solar heating, and this is what is essential for producing motion or kinetic energy, which is what does the transport of the heat upward and poleward. Okay, so along with this, there is poleward transport of heat, which is necessary to keep the balance. And this transport, what is it doing? Basically, by taking the warmer air poleward and upward, and bringing colder air downward and equatorward, you are cooling the tropics and heating the polar regions. This is what we needed, right? We have energy loss at high latitudes, energy gain at low latitudes. So you have to constantly move energy to keep the tropics from getting warmer and warmer with this excess energy. It keeps the poles from getting colder and colder. So combined rotation, radiative forcing, and impact of stratification altogether, you need to determine the role of poleward heat transport in generating eddies. We kept saying there is poleward heat transport needed, and that eddies are doing the work because the angular momentum conservation doesn't work. We generate hydrodynamic instabilities, baroclinic instabilities. The zonal jet becomes unstable and breaks into eddies. So what is the relation between the poleward heat transport and the eddies? If you look at a area along some latitude, you basically want to figure out the heat transport across this latitude, because northward heat transport means across some latitude, right? So the energy that is along a latitude in the azimuthal direction at some latitudes, this is our distance from the local axis of rotation at latitude phi, where we have ignored the z. So A cosine phi lambda is the radial sweep and dz is the height. The associated flux of energy is simply rho v, meridional velocity, times E, the energy density, times dA, the area through which energy is going across the latitude. Okay, just imagine simply northward energy transport. What is the energy here, E? It is our familiar moist static energy CPT plus GZ. These two terms together give us the dry static energy. We add LQ, we get moist static energy plus the kinetic energy of the flow itself, right? 1 over 2 U dot U, or half U squared, the scalar. Okay, so the net energy transport in the Hadley cell is 0. It also has to balance out if you average over the latitudinal circle. So the net heat transport at any latitude across a range of longitudes by the atmosphere is then the integral in the azimuthal direction and in the vertical direction of the meridional transport per unit area, rho v e dA. So again, A cosine phi 0 to 2 pi, full circle for the whole latitude circle, 0 to infinity from surface to the top of the atmosphere, rho v e dz d lambda. This is the azimuthal direction or longitudinal direction. So plug in for rho in terms of the ideal gas law, and you get what did we do here? Rho p dz. So we are using hydrostatic balance. Okay, so just the transport in the Hadley circulation, then energy being lifted from the surface, taken poleward, sinking, and then convergence into the tropics, right? So you can go 2 pi a or g cosine phi. You can look at the appendix and make sure you understood this equation. You're going from 0 to ps, so 0 at the top of the atmosphere to the surface, and v cpt plus gz plus lq dp. What happened? Basically, the kinetic energy term turns out to be very small. It's only like 1 or 2% of the total energy. So all the energy is in the heat and moisture. It's in the moist static energy. It's not in kinetic energy. Winds are strong and so on, but their net contribution to the total energy is very small. Okay, we'll diagnose each term and see exactly what the Hadley cell is actually doing. Is it actually moving a lot of energy northward? Is it part of the energy transport? Is it very efficient in doing that? For doing that, obviously we'll have to see the vertical distribution. Remember, dP is upwards from the surface, and we have to look at the temperature distribution. We have already seen that the temperature gradient is very weak in the upper atmosphere because the Hadley cell itself transports heat and smooths out the gradients. The height of the center of mass is going to contribute something, and the moisture, convection, and moist energy in the atmosphere is going to contribute something. So who is going to do the most work for the Hadley cell? Just how big is the transport, northward transport by the Hadley cell? That's what we will see. Okay, so I will do that in the next podcast. It's not very complicated, but make sure you're following all the concepts. Okay, we did some simple energetic calculations of available potential energy, ratio to kinetic energy, relation to Rossby radius of deformation, and now we are splitting it into energy transport by the Hadley cell, and then we'll see the energy transport obviously by the eddies to the north of the Hadley cell. Okay.